Assalamualaikum warahmatullah, and very good afternoon to all of you guys. Okay, today we have part 3 of the chapter 6. As we have already seen, electrons don't move in straight line paths through a conductor. Instead, they undergo repeated collisions with the metal atoms. Let us consider a conductor with a voltage applied across its end. An electron gains speed as the electric force associated with the internal electric field accelerates it, which gives it a velocity in a direction opposite that of the electric field. A collision with an atom randomizes the electron's velocity, reducing it in the direction opposite the field. The process then repeats itself. You can think of this as analogous to an internal friction force. This is the force of material's resistance. The resistance of an ohmic conductor increases with length, which makes sense because the electrons going through it must undergo more collisions in a longer conductor. A smaller cross-sectional area also increases the resistance of a conductor, just like a smaller pipe slows the fluid moving through it. The resistance is proportional to the conductor's length and inversely proportional to its cross-sectional area of A, where the constant of proportionality ρ is called the resistivity of the material, or equals to ρ times L over A. Every material has a characteristic resistivity that depends on its electronic structure and on temperature, as we can see the values in table 17.1. This table also can be found in our textbook. Good electric conductors have very low resistivities, and good insulators have very high resistivities. Because resistance values are in ohms, resistivities value must be in ohm meter. The resistivity and so the resistance of a conductor depends on the temperature of the metal. For most metals, resistivity increases with increasing temperature. As the temperature of the material increases, its constituent atoms vibrates with greater amplitudes. As a result, the electrons find it more difficult to get by those atoms. Think about trying to walk across a crowded room when people are moving around versus when they are standing still. It's a similar situation with the electrons. The resistance of a carbon filament incandescent light bulb, shown in the figure, increases with the temperature. Over a limited temperature range, the resistivity of most metals increases linearly with increasing temperature according to the expression given here, where ρ is the resistivity at some temperature T in degrees Celsius, ρ0 is the resistivity at some reference temperature at T0, which we usually take to be 20 degrees Celsius, and alpha is a parameter called temperature coefficient of resistivity. Because the resistance of a conductor with a uniform cross-section is proportional to the resistivity, we can write the temperature variation of resistance as shown. The table gives the temperature coefficient for various materials. This is table 17.1. The interesting negative values for alpha for semiconductors arise because these materials possess weakly bound charge carriers that become free to move and contribute to the current as the temperature rises. Let's take a look at the energy transfer in a simple circuit consisting a battery and a resistor. The chemical energy stored in the battery is transformed into kinetic energy of the charge carriers. This kinetic energy is quickly lost as a result of collisions between the charge carriers and fixed atoms in the conductor, which causes the temperature of the conductor to increase. Imagine following a quantity of positive charge, delta Q, through the circuit. We will start at point A here, which is reference point that is grounded, and its potential is taken to be 0. As the charge delta Q moves from A to B through the battery, the electrical potential energy of the system increases by the amount of delta Q times delta V of the battery, and the chemical potential energy in the battery decreases by the same amount. As the charge moves from C to D, the charge moves from C to D through the resistor. It loses this electrical potential energy during collisions with atoms in the resistor. In the process, the energy is transformed to internal energy corresponding to increased vibrational motion of those atoms. We will ignore the very small resistance of the interconnecting wire from B to C and from D to A. So no energy transformation occurs for that stated path. When the charge returns to point A, the net result is that some of the chemical energy in the battery has been delivered to the resistor and has caused its temperature to rise. Okay, now let's take a look at the equation here. The instantaneous rate, delta Q over delta T times delta V, will bring us to the equation of power, P equals to I delta V. We also can calculate the power delivered to a resistor by substituting the Ohm's law delta V equals to IR into the equation of power, will bring us to those two equations, P equals to I square R and also delta V square over R. The power delivered to a conductor of resistance R as an I square R loss. Keep in mind that these two equations apply only to resistors and not to non-ohmic devices such as light bulbs and diodes. Thank you.